Is video clip number 2 about concave mirrors and the images that they form. Um, the other day, or the first one I posted just had to do with some background on some terms, how to understand what's going on the screen, and what to make of the lines and the numbers and all that. So today, or rather with this clip, I'm going to talk about what's true about the images that are formed when the object is located at different positions from the mirror. And we're going to start with the situation that we had on the first clip, where the object is well past the center of curvature. So here is our object out over here. Remember, the object distance, you can see it right here, is 13, which means the object is 13 centimeters from the mirror. Now, where is this compared to the center of curvature? Well, the center of curvature, you can see CC right there, CC. Center of curvature is 8 centimeters. So the object is well past that. Not quite twice as far as the center of curvature, but well past the center of curvature. Also remember that the center of curvature is 2 focal lengths. So the focal point is at 4. That's why the center of curvature is at 8. And the image that is formed of this object by this concave mirror is located between the center of curvature and the focal point. Now that's always going to be true. As you'll see when I start to move this object in just a moment, if the object is out past the center of curvature, anywhere beyond this point, then the image will be located somewhere between the focal point and the center of curvature. If the object moves farther away, I'll move it now, watch where the image goes. See, you get a little closer to the mirror. And if the object moves closer to the mirror, watch the image move farther away from the mirror. So the object distance and the image distance are connected to each other. All right. Now, I'll also ask you to notice the height of the image. As the object moves farther away from the mirror, and I'm trying hard to keep the object height the same. You can look at the object height down here, 1.68. As the object moves farther away from the mirror and stays the same or more or less the same height, you notice the image gets a little smaller. But as the object moves closer to the mirror, and again, I'm trying to keep the object the same height, you'll notice that the image height grows. Oops, got the object a little smaller there, but still you'll see the image height growing. All right. So I'm trying to keep the object about the same, about 1.7, but as the object moves closer to the mirror, the image gets larger. And those two things are a result of the relationship between the image distance, the object distance, and the focal length that we know of from the mirror equation. All right? Okay, so here's my first question. I'm going to put the object at a particular position. Okay, just a little bit farther. Let's see if I can get it exactly on 12. Okay, can't really get it exactly on 12. It's a little difficult to control, but let's see if I can do this. Oh yeah, no, it's still very difficult to control. Okay, so when the object distance is 12, this says that the image distance is 6. Now, what I would like you to do is I would like you to use the mirror equation to solve that. I would like you to take the mirror equation, 1 over f equals 1 over do plus 1 over di, plug in 12 for do, plug in 6 for di, and see if you get 4 for the focal length. You should, right? If this diagram matches with what math we've done, the mirror equation, those two things should work out. Otherwise, somebody's just totally making this up, right? This doesn't make any sense. So see if when the object distance is 12, DO equals 12, 12.01, whatever, and the image distance is 6, see if indeed the focal length is 4 in that mirror equation. Go ahead and pause this, give that a try, and see if it works out. All right, hopefully you saw that that worked out, that the math worked out for that. The next thing I would like you to do, I'm going to change the height of this object a little bit. I'm going to try and make it a nice even number. Oh, look at that. That worked out really nicely. The object height is now 2, exactly 2 centimeters. DO is 12. Oh, it's also exactly right, too. So HO is 2. The height of the object is 2. The object distance is exactly 12. The image distance is exactly 6. Now, what this says is that the image height is -1. Remember, the negative means it's flipped upside down. That's all that tells us. And it's -1 centimeter. And that's the way it looks from this diagram, right? I mean, it looks right, but it shouldn't just look right. The math should work out. So what I would like you to do is to use your magnification equation. Negative DI over DO equals HI over HO. Use the magnification equation from page, what page was it? 468. Use the magnification equation to show that, yeah, that's what the image height should be. If the object is 2 centimeters high and the object distance is 12, and the image distance is 6, then the image height should be -1. Go ahead, pause the video, use that magnification equation to verify that, yep, that's how it works out. That's the way it should be. All right, I'll give you a minute to do that. All right, hopefully you took some time to make sure that that indeed did work out math-wise. I'm going to wrap this clip up in just a moment, but I do want to point out this stuff over here. These descriptions or characteristics of the image formed of this object by this mirror. This is how we describe the image. All right, and we can describe it 4 ways. We can describe its orientation, whether it's inverted, upside down, or upright, right side up. This one is obviously inverted. It is a real image because it is formed at the point where reflected light rays actually intersect. I talked about that in the first video clip. This is the point where reflected light rays actually intersect, so we call it a real image. And of course, real and inverted always go together. We can see that the height of the image is smaller than the height of the object. Like I said before, the image size is smaller than the object size. And that's always going to be true when the object is out past the center of curvature. And also, like I said before, the image is located between the center of curvature and the focal point. As I move the object farther away, it gets closer to the focal point. As I move the object closer to the center of curvature, the image also gets closer to the center of curvature. Now, in the next video clip that I'm going to make, we're going to see what happens when the object is precisely at the center of curvature. But I just want you, before I make that video clip and tell you what happens, I want you to predict what you think is going to happen to where the image is and how big the image is. Look what's happening as I'm moving that object closer. And I want you to predict what will the image distance be and what will the image height be as the object gets closer and closer to the center of curvature. We'll do that in video clip number 3. Thanks, everybody.